as you guys have been paying attention, hopefully, over the last couple days, we've been talking about waves. And I just want to do a quick recap, review, and an ed puzzle just to make sure that you guys have been paying attention. So today I have with me a couple of helpers. I have Hannah and Caleb. They're going to come up here in a little while, and you'll be able to see them shortly. But for right now, let's do a quick recap. What is a wave? A wave is a disturbance that transfers energy from place to place. So if I say, hey, what am I doing? I'm sending a sound wave across the room. I'm transferring that energy from here to there. All right? So a wave is anything that transfers energy from place to place. We see waves in the ocean. We see waves. We talk about sound waves. We talk about light waves. And we even talk about a wave. It's transferring energy from one place to another. All right, so that's a wave. It's easiest when we draw transverse waves. So I'm going to show you what that means really quickly, and then we'll talk about the parts of it. So could I have my friends to come on up here real quick? You hold that side. You hold that side. Step in a little closer so they can see all your lovely faces. There you go. So we're going to use a slinky, and I'm going to model a transverse wave. So if you were to move that to cause a disturbance, you're going to move that to make a wave. So it's going to go like that. That's slow motion, right? Do it again. What? Now freeze that for just a second. Could you hold that part right there? Thank you very much. This is going to be called a crest. The very top, the tippity top of a wave is called a crest. All right? A crest. The lowest part, the one down here, the farthest away from rest, is called a trough. We're going to go through that again in just a second, so we're going to let go of that. Perfect. Thank you very much for right now. You want to hold that for a second? Perfect. Thank you very much. So if I were to draw that, here's my wave. So whoosh, wave, right? So the energy is moving from here to here. This part of the wave is called a crest. My first name is Tara. And when I was a kid, I asked my parents what my name meant. And I remember my dad saying, oh, your name is Tara. And it means the fertile soil on the very crest of the mountaintop. So I'm named for dirt, so that's fine, but whatever, okay. So, but it helps me to remember that that's the top of the mountaintop, the crest. Now, if I were, say, to go to a farm and I had all these animals around and I had to like feed the animals or fill it up with water, I might say I have to fill up the what? With water. The trough, right? The trough is the lowest part of a transverse wave. And if you could kind of picture, I could fill that up with water. See, that's my trough. So this guy right here is called a trough. All right, so I have my crest, I have my trough. Now, just to kind of get it in our heads where we start from, I'm going to make this dotted line. And this dotted line right here represents our medium, in this case, our slinky, at rest. And here comes the wave, right? And it's, so here's my crest, here's my trough, here's my point of rest. All right. We're going to quickly go over now the properties of waves. All waves have 4 properties and they go like this. We're going to start with amplitude. So our amplitude is the distance between the point of rest and either the top or the bottom of the wave. So if I were to measure it, we'll go like this. Here's my point of rest, my medium before it's been disrupted. Here's my lowest point, my trough. That's my amplitude. If I were a perfect artist, this would be exactly the same distance is this right here. I'm obviously not a perfect artist, but you get the idea. Distance from rest. So could I get my my friends Hannah and Caleb to come back up here again? I want you to hold the slinky over there. I want you to hold the slinky over here. I want you to hold it up so the beautiful screen can see the slinky. This is what I want you to do. You ready? Give me a low amplitude wave. All right. Now give me a high amplitude wave. All right. Now what was the difference? High amplitude, bigger disturbance. Bigger disturbance results in a higher amplitude wave. Excellent. My next, well, let me go ahead and throw this up for you real quick. My next property of waves is wavelength. And that's exactly what it sounds like. It's the length of the wave. A wavelength is going to be the distance between the same point of wave to the next same point of the wave. For instance, trough to trough, that's my wavelength. Or crest to crest, that's my wavelength. Or beginning of this wave at the point of rest to the beginning of the next wave at the point of rest. And again, if I were a perfect artist, all three of these would be exactly the same length. We can manipulate the wavelength basically by moving our disturbance faster. Can I grab you again? And I'm going to have you go over there to the other side of the chair this time. I'm going to spread it out a little bit more and go a little higher. If I want a single wave, you can see that transfer of energy from one point to the other. If I want one big wave, right, there's my long wavelength. And if I want, I'm going to stop it for a second. And if I want a shorter wavelength, I just have to move my disturbance and short a little burst of energy. Perfect. Thank you, my friend. All right, so that's my wavelength. A third property is frequency. This is where it kind of gets, I think, a little bit fun. So you get to see my incredible artistic ability as I talk about frequency. Frequency is the number of complete waves that pass a given point in a certain amount of time. So let's say I'm sitting at the end of a pier and I'm looking sideways at the ocean and the ocean's moving. Ooh, look at the waves. And I see out in the ocean maybe a boat or a buoy or maybe a seagull. Oh, it's easier to draw a boat. Yeah, we'll draw a seagull. All right, so here's my seagull right here and he's sitting on the ocean and let's give him a little body here. See if this marker is any better. Here's a little head. Here's his beak. Seagulls have beaks, right? Yep. Couple of feather. Oh, you get the idea. All right. So what's his name?
Bob.
Bob. Let's call him Bob. I like Bob. That's great. So here's Bob right here, and we're going to use Bob as our point of reference because it's really hard to count waves as they're going by without some kind of a point of reference, that point that doesn't move. So in this case, we're going to look at Bob. As the wave comes by, does it pick up Bob and throw him onto the shore? No. What happens to Bob? He just kind of bobs. Yeah, you get it? Yeah, right? Okay. So here's Bob, and let's say here comes the ocean waves, and Bob is moving about 1 bob a second. He's moving at a frequency of 1 wave per second. You with me so far? Now what if he's going a little faster? Waves, storms picking up. Maybe he's going 2 waves a second. One thing about science though, math as well, is we don't like to use units of measure like 2 waves a second. Because it doesn't really mean anything if we don't really know what a wave is or how big the wave is. So we need a standard unit of measure. And in science, when we're measuring frequency, we're going to use Hertz. Hertz is not plural. Hertz ends with a Z, so a single Hertz is not a single Hert, okay? It's a Hertz. So if Bob is bobbing at 1 bob a second, 1, 2, 3, 4, over the course of 4 seconds, you get it? He would be going 1 bob or 1 wave per second, which we would write that as 1 Hertz. You get it? Hertz is just a unit of measure. It's nothing fancy, it's just the unit of measure. But just like we don't say, oh yeah, I went 500 kilometers per 3 hours. We don't say that, right? We say, you know, I went X amount per 1 hour. We're going to do the same thing. So let's say Bob here is bobbing 3 bobs a second. 1, 2, that wave, man, it's just picking up. You might say that's 3 Hertz, right? 3 bobs per second or 3 waves per second, 3 Hertz. But after the storm, and it starts calming down, and Bob is slowly bobbing. And let's say it takes a full 2 seconds for 1 wave to pass. Well, I would look at 1 wave per 2 seconds. So what would my Hertz be? Be 0.5. 0.5 Hertz. You with me so far? Got it? All right. Okay. So let's go ahead and look at Bob again. And let's see how fast the waves are as they pass Bob. Now, here are the things you need to know. First of all, this is our fourth property of waves, and that's speed, how fast a wave is traveling. Now remember that speed is equal to distance divided by time, like meters per second, or miles per hour, or kilometers per hour, right? But when we're looking at a wave is not a standard unit of measure. A wavelength is what is going to be equivalent to distance. But if I were to try to figure this out, I would have to take my wavelength, which is always measured in meters. Let's say it was 0.5 meters, okay? And then I would take my time, but I can't really distance. What's my time of a wave? That doesn't really make sense because a wavelength is always changing. How many? Oh, that's right. That's standard unit of measure, Hertz. What a Hertz is, though, is it's a wavelength divided by, or what speed would be then would be a wavelength, which is my distance, divided by the wave number, divided by the time it took to go through. When I take a division problem and a division problem, the easiest way I could do that is to flip the second division problem and multiply across, which is basically what I'm going to do. I'm going to look at this, I'm going to kind of X that out, and I'm going to look at just the Hertz because we've already done the division problem for Hertz, right? We've already taken that waves per second. So now I'm going to look at wavelength times my Hertz to get my speed. So let's say Bob, his wavelength was, let's say, 1 meter, and he was bobbing at like 3 bobs a second, so that's my 3 Hertz, right? So I would just take my 1 meter, I'd multiply it by my 3 Hertz. What would the speed of my wave be? 1 meter, or excuse me, 3 meters per second. So that would simply multiply. All right? With me so far? All right, cool. But let's recap. Like, why are we learning about this stuff? What does this have to do with anything? Well, I'm going to show you how waves, we can't always see the waves with Bob or the ocean waves. But the very first thing we're going to focus on outside of Slinkies and Bob is going to be sound. So let me show you something. I'm going to be talking to you right now at a moderate voice. It's going to be fine. And what I'm doing right now is I'm making waves, the disturbances in my vocal cords that are disturbing the air particles around, that are sending those compressed air particles out as waves. How would I be able to increase my amplitude? Well, when you guys were doing your Slinkies and I asked you to increase the amplitude, what did you do? You went bigger, right? Little and then big. So if I wanted to increase the amplitude of my voice, I would yell, I would raise my voice, and I would cause a bigger disturbance in my vocal cords. What about if I wanted to adjust my wavelength? It's kind of hard to imagine this. So what I want to show you is if I could get you guys to come back on up here. I'm going to have you hold this guy, you hold this guy, spread out just a little bit, spread out a little bit. And I think I might need to adjust my camera for this. So I'm going to go ahead and take you guys on a little walk. All right. Now, it's hard to adjust my wavelength unless I'm thinking of increasing something else. So here we go. You ready? Give me one wave, just a slow disturbance, up and down. Keep going, keep going. All right. How big is that wavelength? A couple meters, right? Let's say I wanted to make a smaller wavelength. If you guys can't move, how can I make waves with a smaller wavelength? Go faster. Go ahead. Keep going, keep going, keep going. Yes! Now I have 3 waves. By increasing the frequency, I shorten my wavelength. It's all mathematical. I'm not changing, I can't change the speed that the wave travels, but I can increase the frequency, which will shorten the wavelength. And if you get it going really well, yes, like that, you can see distinct 1, 2, 3. And if I was trying to count what my Hertz is right here, I bet I would have a much higher count than if I slowed down my amplitude. Slowed down my frequency. 1, 2, 3, 4. Now speed it up. And as they speed it up, again, more waves appear. Do you see how they're related? Now, how does that then translate to my voice? If I can increase my amplitude by getting louder, how can I increase or decrease my wavelength? To decrease my wavelength, I have to increase my frequency. Does that make sense? So, what I could do with my voice is I have to vibrate this faster. So my vocal cords, I have to vibrate faster. How can I do that? It's kind of like playing a guitar, right? Dun, 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 dun. Right? You get that really short string, and it makes it vibrate faster. You tighten your vocal cords, and all of a sudden, I'm speaking really, really high pitch. By the way, when it comes to sound, pitch is related to frequency. The higher the frequency, the higher the pitch. And the lower the frequency, the lower the pitch. Hi, I'm Johnny Cash. All right. Now, how then can I change the speed of my sound? How can I change the speed of my sound? How can I make my voice reach you more quickly?
You can't.
You can't. The speed of waves is set. The speed depends on the medium, which is the stuff that the wave is moving through, which also happens to be, let's see, our next vocabulary word. I'm going to give you that in just a second so I can move my camera up at the same time. Swoosh. Swoosh. All right. Medium. That's the stuff that the sound travels through, or the wave in general travels through. Right now, the sound is traveling through air. Okay? It's invisible, but it's still there. As I'm talking, it's compressing the air. If there was no air, if there was no air, you wouldn't be able to hear anything. If I yelled in space, you wouldn't hear me because there's no air. There's no particles for it to travel through. In space, no one can hear you scream. All right. So far we've been talking about something called a transverse wave, and that's the wave that moves the medium perpendicular to the direction of the energy of the wave. So as the wave is moving this way, the medium is simply moving up and down. And you can tell that when you've got your slinky. And maybe the wave is going this way, it's going this way. But the median, this coil right here that I'm looking at right in front of my eyes, no matter what's going on here, that median is just going up and down. Okay, that's a transverse wave. I always start by teaching transverse waves because it's the easiest to write things like crest and trough, etc. Easiest to understand that. The second kind of wave, though, the one we're going to be talking about when we're talking about sound, is called a longitudinal wave. I like the word longitudinal. It's the one that reaches out. A longitudinal wave you might remember from earth science when you're talking about earthquakes. It's the primary wave. It's the one that happens first. It's a wave that moves the medium parallel. Hey! And it compresses the air in front of me and it shoots out like this. Not like this, like this. It's that primary wave. As an earthquake, the primary wave is the start, and the transverse waves, the secondary waves, actually do the most damage. But the longitudinal wave moves the medium parallel. Hey! I yell, and the median is moving back and forth. Now, longitudinal waves do not have crests, and they do not have troughs. They have something different. Instead of a crest, they have a compression. The root word to compression is press. Why do you think that is? Well, let's check it out. I'm going to have you come on up here. You're going to hold this for me. You're going to hold it really close to the camera like this. Let's see, tilt it forward a little bit. Let's see if we can see this real quick. You ready? Transverse waves go up and down. Compression waves or longitudinal waves go a little bit flatter. There you go. It's kind of hard to see. There you go, that's a good one. It moves the median, in this case the coils, back and forth. So could I get Caleb to come up here for a second? Caleb, can you just hold this guy right here? Yep. So if I could do this in slow motion, right? I would move the medium back, I would push it forward, and it would press the coils together, which would press the coils in front of that, which would press the coils in front of that, which would press the coils in front of that. And that pressed wave is called a compression. So I say, hey, and it presses the particles in front of me, which presses the particles in front of them, which presses the particles in front of them. That's a compression. And again, if you can see that coil, as the wave went through, it's going back and forth, back and forth, back and forth, not up and down, up and down, up and down. So the part of the longitudinal wave where the particles of the medium are close together is called compression. So if I were to draw this, this is how I would do it. These are my air molecules. Here's all my air molecules close together. And now they're spread out again. As a slinky, it might look like this. You get it? Pressed together. Pressed together by compression. My rarefaction is the second part. My rarefaction, again, look at the root word. In this case, the root word is rare. When it's hard to find something, it's rare. So as the particles are spread out, this is called your rarefaction. Compression, rarefaction. So let's say that here's my second wave. How am I going to measure my wavelength? From one point of my compression to the next same point of my compression. That's my wavelength in a longitudinal wave. My frequency would be how many compressions there are at a given point in time. My speed would be how many compressions pass a point at a given time. My amplitude is how squished that air is. So if I say, hey, I'm really squishing that air in front of me. Well, friends, that was a long one. Thank you for joining me through all of this, and thank you so much to my wonderful, fabulous assistants. Come on up here and take a bow. Come on, come on, come on. Thanks, guys.